So, have you ever wondered what's really going on deep inside your computer? I mean, what are the absolute fundamental rules that make all our technology tick? Today, we're prying open the instruction manual for literally every computing device out there. We're talking about the theory of computation, really, the blueprint for thought itself. And let's just get right to the heart of it with a huge question. Are there problems that are just impossible to solve? Not because our computers aren't fast enough, but because they are logically impossible for any computer ever to figure out. That's a pretty wild idea, right? Now, for this explainer, our source material is, well, it's a little different. We're not digging through research papers. We're using the secret blueprints themselves. Years and years of university computer science exams. These papers hold the core challenges, the absolute fundamentals that every computer scientist has to master. And they're going to be our map for this journey. Okay, so to figure out the limits of what a computer can do, we first have to agree on what a computer even is. So here's what we're going to do. We're going to build what I call a ladder of computation, starting at the bottom with the most basic machine you can possibly imagine. So, say hello to the first rung on our ladder, the finite automaton. You can think of it like a super simple vending machine. It's got a few states it can be in, like waiting for coins, ready to sell, sold out. And here's the key. It has zero memory. It only knows what state it's in right now. You put a coin in, it changes state, and that's it. At the end, it either accepts what you gave it and gives you a soda, or it rejects it. Simple as. So, what can you do with a machine this simple? Well, here's a classic problem we pulled straight from one of those exams. The challenge is to design one of these little machines, a DFA specifically, that can spot a really specific pattern. Any string of letters that has exactly one letter A in it. And check this out. This diagram is the solution. It's not code. It's a visual map of the machine's brain. The circles are the different states, like, I haven't seen an A yet, or I've seen exactly one A. The arrows show you how it jumps between states depending on the letter it reads. And if it ends up in that special double circle, boom, the string is accepted. It's just pure, simple logic made visible. Pretty cool, huh? Now, these simple machines, and trust me, they're all over these exams, come in two main flavors, mealy and more. And the difference is all about timing. A mealy machine spits out an answer based on where it is and the immediate input it just got. But a more machine, it's a little more chilled out. Its output only depends on the state it's already in. It's a small difference, but it's absolutely crucial when you're trying to design really stable and predictable systems. Okay, but let's be real. A machine with no memory isn't all that useful. What happens when it needs to, remember things? So let's climb up to the next rung on our ladder and give our little machine an upgrade, a simple memory. And that brings us to the Pushdown Automaton, or PDA for short. It's basically our finite automaton from before, but now it has a superpower, a stack. So what's a stack? Just picture a stack of plates in a cafeteria. You can only put a new plate on top, and you can only take a plate from the top. You can't just grab one from the middle. It's a last in, first out kind of memory. So why does a stack matter? Well, take a look at this next challenge, another classic from the exams. The goal is to recognize a pattern where you have a bunch of A's followed by the exact same number of B's. Our simple little vending machine can't do this. No way. It's got no memory, so there's no way for it to count the A's to make sure they match the B's. But our new machine, the PDA, can handle it no problem. Here's the trick. For every single A it reads, it just pushes a little token onto its stack of plates. Then, for every B it sees, it pops one of those tokens back off. If it gets to the end and the stack is perfectly empty, it knows the count's matched, and it accepts. This right here is basically how your code compiler checks to make sure all your parentheses and brackets match up. It's fundamental. All right, we've had a machine with no memory and one with a simple memory. Now it's time, let's go all the way to the top of the ladder and meet the big one, the theoretical machine that is so powerful it defines the very meaning of the word computable. This is it, the Turing machine. Alan Turing dreamed this up way back in 1936. And it's shockingly simple. All it is an infinitely long tape, kind of like a roll of film, a little head that can read and write on the tape, and a simple set of rules. That's it. But here's the mind-blowing part. Despite its simplicity, this machine is powerful enough to simulate any algorithm that could ever be run on any computer. This is the gold standard. So how does this ultimate machine actually think? It's just a simple little dance, repeated over and over. First, the head reads whatever symbol is on the tape right below it. Then, based on that symbol and whatever state it's in, it looks up in its rulebook what to do next. The rulebook tells it 3 things: what to write on the tape, whether to move left or right, and what new state to switch to. And then it just does it all over again. That's it. With just those simple steps, it can compute anything. So, we made it. We're at the top of the ladder. We have a machine that can solve any problem that can be solved. But the view from up here is a little bit shocking, because having this ultimate machine doesn't just show us what's possible, it finally shows us what is truly, fundamentally impossible. And this is really the climax of the whole story. It's a theme you see over and over in these exam questions. After inventing this perfect, all-powerful machine, Alan Turing did something brilliant. He turned its incredible power back on itself and asked a question that would change the world of computing forever. And the question sounds pretty simple. Could you write one master program, let's call it a halting detector, that could look at any other program you feed it and tell you with absolute 100% certainty, will this program eventually finish its job and stop, or is it going to get stuck in an infinite loop and just run forever? Well, here's the kicker. When you try to build that program, you run headfirst into a paradox you just can't escape. Just imagine you write a sneaky little program that feeds its own source code to your detector. And this sneaky program is designed to do the exact opposite of whatever the detector predicts. So if the detector says, yep, it'll halt, the program goes into an infinite loop. If the detector says it'll loop forever, the program immediately halts. See the problem? No matter what the detector says, it's going to be wrong. So a perfect detector is logically impossible. And this famous paradox has a name, the halting problem. And in computer science, it is proven to be undecidable. That's the official term. It means there is no, and there can never be, a single general-purpose algorithm that can solve this problem for every possible program. This isn't a limitation of our current technology. It's a fundamental limit of logic itself. So, okay, we've got these abstract, theoretical machines and a problem that can't be solved. Why should you care? What does this have to do with anything today? Well, it turns out these weird blueprints from the 1930s are the absolute bedrock that all of modern computing is built on. This table, the Chomsky Hierarchy, really ties our whole journey together. It's a central idea from our exam sources, and it's like a grand blueprint for computation. It shows this beautiful, clean relationship. For every type of language, from the simplest to the most complex, there's a perfectly matched machine with just the right amount of power to understand it. It's the theory that lets us build everything from a text search to a complex programming language compiler. And this theory isn't just about history. It helps us classify how hard problems are to solve. And that leads us straight to one of the biggest, most important unsolved mysteries in all of science, which also shows up in these exams, P versus NP. Basically, it asks, if checking the answer to a puzzle is easy, like looking at a finished Sudoku, does that mean finding the answer is also easy? We all think the answer is no, but no one can prove it. If the answer were yes, it would change everything. Most modern encryption would become useless overnight. Which leaves us with a final, massive thought to chew on. The theory of computation proved that there are real, hard boundaries to what we can know through calculation. The halting problem isn't an engineering bug we need to fix, it's a feature of logic in our universe. It suggests that some questions, some truths, might simply be unreachable by any step-by-step process. And that is a truly profound idea.